The paper introduces a novel approach to address the binding problem in machine learning, which is the challenge of representing and connecting objects within a fixed network of neural connections. It proposes an alternative to slot-based methods, which have limitations due to their discrete nature and difficulty in expressing uncertainty. The authors introduce rotating features, a generalization of complex valued features to higher dimensions, and a new evaluation procedure for extracting objects from distributed representations. This approach enables the discovery of objects in real-world data, advancing the paradigm for addressing the binding problem in machine learning. The authors propose an extension to standard features by adding an extra dimension, termed rotating features, which enables the representation of object affiliation and presence across the entire architecture. This is achieved by setting up the layer structure such that the magnitudes of rotating features learn to represent the presence of features, while their orientations learn to represent object affiliation. Unlike the Complex AutoEncoder, CAE, which is limited in its ability to separate object representations and is only applicable to single-channel inputs, the proposed rotating features can scale to real-world data and represent a greater number of objects simultaneously. The contributions of this paper include the introduction of rotating features, a generalization of complex valued features to higher dimensions, which requires the development of a new rotation mechanism. Additionally, a new evaluation procedure for continuous object-centric representations is proposed, enabling the extraction of discrete object masks from continuous object representations of inputs with more than one channel, such as RGB images. Furthermore, the authors demonstrate the applicability of their approach to features created by a pre-trained vision transformer, allowing rotating features to extract object-centric representations from real-world images. In the realm of machine learning, previous research has drawn inspiration from neuroscientific theories to implement two message types using complex valued features. These features' magnitudes encode feature presence, and their relative phase differences encode feature binding. However, these approaches are limited by unidimensional orientation information and lack evaluation procedures that scale beyond single-channel inputs, restricting them to grayscaled toy datasets. To overcome these limitations, the proposed method introduces several advancements for distributed and continuous object-centric representations. The proposed approach, named rotating features, extends standard features into n-dimensional vectors, creating a feature matrix Z rotating element of Rn times D. The magnitude vector of this matrix, Z rotating 2, behaves similarly to a standard feature vector and learns to represent the presence of certain features in the input. The remaining n1 dimensions represent the orientations of the rotating features, which the network uses as a mechanism to bind features. Features with similar orientations are processed together, while connections between features with different orientations are suppressed. The representation of rotating features in Cartesian coordinates rather than spherical coordinates avoids singularities that may hinder the model's ability to learn good representations. This is because spherical coordinates can lead to singularities due to dependencies between the coordinates, particularly when a vector's radial component, magnitude, is 0. Allowing the angular coordinates to take any value without changing the underlying vector. As the network applies ReLU activations on the magnitudes, this singularity may occur regularly, hindering the network from training effectively. The proposed advancements for distributed and continuous object-centric representations aim to scale beyond single-channel inputs and evaluate real-world datasets. By implementing a series of advancements, the model can be applied to real-world images, as demonstrated in Figure 2. This figure showcases the application of rotating features on real-world images, highlighting the model's ability to segment objects effectively. In the rotating features processing layer, a novel binding mechanism is employed to ensure that features with similar orientations are processed together. This is achieved through a neural network layer with shared weights across rotation dimensions and unshared biases, facilitating a unique orientation offset for each feature. The binding mechanism is implemented by integrating the weights with the magnitudes of the input features, resulting in the selective processing of features with similar orientations and the suppression of those with dissimilar orientations. This process is visually represented in Figure 3, which illustrates the binding mechanism's effect on feature processing. By processing features in streams, This mechanism enables the network to create object-centric representations, leading to the emergence of object-centric representations. In the realm of machine learning, the development of efficient algorithms for processing large datasets has become a crucial aspect of data analysis. One such algorithm, the alternating direction method of multipliers, ADMM, has gained significant attention in recent years due to its ability to efficiently solve optimization problems. ADMM operates by iteratively updating primal and dual variables, leveraging the augmented Lagrangian function to ensure convergence. The algorithm's efficacy is rooted in its ability to exploit the problem's structure, thereby reducing the computational complexity. A novel approach to ADMM, proposed by researchers, involves the incorporation of a proximal term in the augmented Lagrangian function. This modification enables the algorithm to tackle non-convex optimization problems, a feat previously unachievable with traditional ADMM. The researchers' findings indicate that the proximal ADMM algorithm outperforms its traditional counterpart in terms of convergence rate and accuracy. The algorithm's performance is further underscored by its ability to handle large datasets, a critical aspect in modern data analysis. The paper's results are substantiated by numerical experiments, which demonstrate the algorithm's efficacy in solving non-convex optimization problems. The authors also provide a comprehensive analysis of the algorithm's convergence properties, further solidifying its validity. A key limitation of the proximal ADMM algorithm lies in its reliance on the proximal term, which can be computationally expensive to evaluate. Future work involves developing strategies to mitigate this limitation, thereby enhancing the algorithm's overall efficiency. In conclusion, the proximal ADMM algorithm represents a significant advancement in the field of machine learning, offering a powerful tool for tackling complex optimization problems. In the realm of unsupervised representation learning, a crucial challenge lies in object discovery and reconstruction from complex datasets. To address this, researchers have proposed rotating features, RF, a novel approach that leverages rotational invariance to enhance feature extraction. This study compares the performance of RF with standard autoencoders, A, and complex autoencoders, CAE, on the 4Shapes dataset, a benchmark for object discovery tasks. The experimental setup employs a convolutional autoencoding architecture, trained using an atom optimizer with a learning rate of 0.001 and a batch size of 128. The evaluation metrics include mean squared error, MSE, for reconstruction quality and adjusted RAND index, RE, for object discovery performance. The results show that RF outperform A and CAE in terms of reconstruction quality, producing sharper images with more accurate object boundaries. Notably, RF exhibits superior object discovery capabilities, particularly when the rotation dimension n is 6 or higher. This is attributed to RF's ability to capture rotational invariance, enabling the model to learn more robust and informative features. The study's key findings highlight the advantages of RF over baseline methods, including improved object discovery and reconstruction capabilities. These results have significant implications for applications such as computer vision, robotics, and image processing, where robust feature extraction and object discovery are essential. Rotating features, a novel representation method, outperforms the convolutional autoencoder (CAE) model in object representation, particularly in scenarios with multiple objects. To investigate this, the study utilizes two datasets, 4Shapes and 10Shapes, comprising grayscale images featuring 4 and 10 shapes per image, respectively. The results show that as the rotation dimension increases, the performance of rotating features improves, achieving perfect separation of all 4 objects in the 4Shapes dataset at n equals 6. Moreover, it successfully differentiates 10 objects simultaneously in the 10Shapes dataset, demonstrating its scalability. The study also explores the applicability of rotating features to multi-channel images by creating an RGB version of the 4Shapes dataset, where each object is randomly assigned a color and depth value. The findings indicate that rotating features struggle to distinguish objects in the RGB version when the number of potential colors increases, as they tend to group different shapes together based on shared color. However, with the addition of depth information, rotating features successfully separate all objects. The proposed evaluation procedure makes rotating features applicable to multi-channel inputs, but requires higher-level information in the inputs to reliably separate objects. This is supported by applying rotating features to commonly used object discovery datasets, multi-DS sprites and CLEVR, where the same problem occurs without depth information. Furthermore, the research applies rotating features and the proposed evaluation procedure to real-world images by utilizing the features of a pre-trained vision transformer, highlighting their potential in practical applications, particularly in scenarios where object discovery is crucial. The application of rotating features on RGB and RGBD images for object discovery is discussed, highlighting the effectiveness of adding depth information to resolve the issue of grouping objects of the same color. The setup utilizes a pre-trained Dino model and an auto-encoding architecture. Results on the Pascal VOC dataset show that rotating features outperform the baseline and some other models, indicating a good separation of objects. The performance on the FoodSeg 103 dataset further demonstrates the scalability of rotating features to real-world settings. The rotating feature's ability to separate objects through unsupervised training is a significant contribution. The summary begins by focusing on the clustering methods and their efficiency on the Pascal dataset. It highlights the benefits of rotating features, including their ability to automatically distinguish the correct number of objects, generalize well to different numbers of objects, express uncertainty in object separations, and efficiency in running. The section on clustering methods emphasizes the ease of evaluating various methods and hyperparameters after training. The summary then delves into the generalization performance of rotating features, showcasing their ability to maintain stable performance across varying numbers of objects in test images, even when the number is unknown. This performance is compared to slot attention, highlighting rotating features' efficiency and adaptability. In this research, the authors introduce a novel approach to object-centric representation learning through the concept of rotating features. This method aims to solve the binding problem in machine learning by creating continuous and distributed object-centric representations. The proposed model, when combined with pre-trained features, demonstrates scalability and expressiveness in addressing the binding problem, particularly in real-world data. The authors evaluate their approach using a new evaluation procedure and compare it against existing state-of-the-art models such as slot attention and dinosaur. They find that rotating features outperform other models when evaluated with k-means clustering, especially as the number of objects in test images increases. However, they observe that the performance of the slot attention model and the rotating features model evaluated with k-means clustering decreases significantly as the number of objects in the test images increases. This issue can be mitigated by evaluating the rotating features model with agglomerative clustering, which preserves a fairly consistent performance across varying numbers of objects in each scene. The authors also explore the concept of uncertainty maps, revealing higher uncertainty in areas of object overlap, object boundaries, and incorrect predictions. They note that the training time for the presented rotating features model on the Pascal VOC dataset is less than 3.5 hours on a single NVIDIA GTX 1080 Ti, making it more efficient than other models like Dinosaur, which require 8 NVIDIA V100 GPUs. The paper discusses related work in the field, highlighting various approaches to solving the binding problem, including slot-based object-centric representations and continuous and distributed methods. It emphasizes the novelty of the proposed paradigm for object-centric representation learning and encourages further innovation and research in this area. In conclusion, the authors propose a new approach to object-centric representation learning that leverages rotating features, a new evaluation procedure, and higher-level input features. While the proposed model has some limitations, such as the capacity to represent more objects at once and the need for further research into novel inference methods, it demonstrates promising results in addressing the binding problem in machine learning and offers potential for future advancements in the field. Acknowledgements and disclosure of funding are provided, citing insightful discussions with Jascha Sol-Dickstein and Sjoerd van Steenkist, and Francesco Locatello's work outside of Amazon. Sindy Löwe was supported by the Google PhD Fellowship. The research benefited from collaborative discussions and external support, highlighting the importance of interdisciplinary interactions in advancing knowledge. Object representations, scene understanding, and neural networks are crucial components in machine learning research. One notable approach is ArXiv, a method that infers unordered object representations without relying on iterative refinement. This is achieved by leveraging a neural network that outputs a set of object representations in a single pass, eliminating the need for iterative refinement. Another approach is attend, infer, repeat, a fast scene understanding method that utilizes generative models. This method involves attending to relevant regions in an image, inferring object representations, and repeating this process to build a comprehensive scene understanding. The Pascal Visual Object Classes (VOC) challenge is a prominent benchmark for object classification tasks, highlighting the importance of accurate object classification in scene understanding. Cognitive dynamics also play a critical role in scene understanding, with Pascal Frey's work introducing the concept of neuronal coherence. This concept describes the synchronized activity of neurons in the brain, which is essential for information processing and cognitive tasks. Unsupervised learning of temporal abstractions is another area of research, where neural networks are trained to extract meaningful patterns from temporal data without human supervision. Neural production systems, which combine symbolic and connectionist AI, are also explored as a means to represent and manipulate complex knowledge structures. Furthermore, matrix capsules with M-routing have been proposed as an effective method for unsupervised image classification and segmentation. This approach leverages capsule networks to capture complex spatial relationships between objects, and M-routing to iteratively refine the segmentation results. Additionally, invariant information clustering has been shown to be effective in unsupervised image classification, where the goal is to discover underlying patterns and structures in the data without prior knowledge of the class labels. This page presents a comprehensive list of the methodologies, algorithms, and mathematical concepts employed in the research. It begins with an in-depth explanation of the data collection process, which involved gathering information from various sources and applying rigorous quality control measures to ensure accuracy and reliability. The text then delves into the statistical analysis techniques used to identify patterns and trends within the dataset. These include regression analysis, hypothesis testing, and confidence interval construction, all of which are essential for making precise predictions and drawing conclusions about the research findings. In addition to statistical methods, the page also discusses the application of machine learning algorithms to further refine the data analysis. These algorithms, such as decision trees and neural networks, were utilized to identify complex relationships between variables and make predictions based on the data. Furthermore, the page provides an overview of the mathematical models developed during the course of the research. These models, grounded in probability theory and linear algebra, were designed to simulate real-world scenarios and predict outcomes under different conditions. The page concludes with a detailed description of the limitations and assumptions inherent in the study, as well as suggestions for future work. This includes potential avenues for further research and improvements to the methodologies and algorithms used in the study. Overall, this page serves as a valuable resource for researchers seeking to understand the technical details of the research and its implications for the field. The authors present a comprehensive list of 17 distinct graph neural network architectures, categorized into 3 primary groups: spectral-based, spatial-based, and hybrid approaches. These architectures are designed to tackle graph-structured data, leveraging graph convolutional neural networks, graph attention networks, and graph autoencoders to process node, edge, and graph-level features. The spectral-based approaches, including ChebNet and GCN, operate in the spectral domain, exploiting graph Laplacian properties to define convolutional operations. Spatial-based methods, such as GraphSage and GAT, focus on node neighborhoods, aggregating features through spatially aware mechanisms. Hybrid models, like graph attention networks and diff pool, combine spectral and spatial techniques to capture both local and global graph properties. The authors provide a thorough analysis of each architecture, detailing their strengths, weaknesses, and applications in tasks such as node classification, graph classification, and link prediction. This comprehensive survey facilitates a deeper understanding of the graph neural network landscape, enabling researchers to select the most suitable architecture for their specific problem domains. The authors also highlight the importance of considering the trade-offs between model expressiveness, computational complexity, and interpretability when selecting a graph neural network architecture. By providing this systematic review, the authors aim to stimulate further research in the development of novel graph neural network architectures and their applications in real-world problems. This study presents a systematic review of existing literature on deep learning-based methods for medical image segmentation. The authors conducted a thorough analysis of 135 papers published between 2010 and 2022, focusing on convolutional neural networks, CNNs, and their variants. The review highlights the strengths and limitations of various CNN architectures, including UNet, SegNet, and FCN, in segmenting different anatomical structures from medical images. The authors also examine the impact of various image preprocessing techniques, data augmentation strategies, and loss functions on segmentation performance. Notably, the study reveals that while CNNs have achieved state-of-the-art performance in medical image segmentation, there are still significant challenges to be addressed. These include the need for larger, more diverse datasets, improved model interpretability, and better handling of class imbalance and noisy labels. The authors also identify future research directions, such as exploring the potential of transformers and graph neural networks for medical image segmentation, and developing more robust evaluation metrics that can accurately assess model performance in real-world clinical settings. By providing a comprehensive overview of the current state of deep learning-based medical image segmentation, this study aims to inform and guide researchers and practitioners in the development of more accurate and reliable segmentation algorithms for clinical applications. The research concludes by highlighting its broader impact on machine learning, potential biological insights, and improved model interpretability. It emphasizes the importance of continuous object-centric representations for complex data, addressing scalability and real-world applicability. The paper provides a statement on reproducibility, detailing model architectures, hyperparameters, evaluation procedures, datasets, and baselines used. The implementation details section outlines the auto-encoding model's architecture and hyperparameters, including activation functions and parameter counts. The paper acknowledges potential unforeseen consequences and emphasizes the need for further innovation and interdisciplinary collaboration. The auto-encoding architecture for models trained on raw input images and those applied to pre-trained DINO features is outlined in the page. These models' hyperparameters include training steps, batch size, learning rate warm-up steps, peak learning rate, gradient norm clipping, feature dimension, rotating dimension, image, crop size, cropping strategy, augmentations, and the number of augmentations applied. The architecture consists of several layers, starting with an input layer followed by a series of convolutional and transposed convolutional layers. For models applied to DINO features, additional layers are included, marked by an asterisk, which are not present in models trained directly on raw images. The hyperparameters for models with rotating features that are trained directly on raw input images are detailed in Table 3, including datasets such as 4 shapes RGB, D, and 10 shapes, each with its own set of hyperparameters. Similarly, Table 4 provides the hyperparameters for models trained on DINO features. The use of a pre-trained vision transformer model, specifically the DINO model from the TIM library, is also discussed. This model is used to generate higher-level input features of real-world images before feeding them into the rotating features model. The final output of the transformer block is used as input for the rotating features model, excluding the last layer norm and the CLS token entry. The Pascal FoodSeg 103 dataset, utilizing DINO preprocessed features, is trained on models with rotating features. This setup closely follows Seetzer et al. 64 for comparability. The training process involves 5,000 steps, a batch size of 256, learning rate warm-up over the first 1,000 steps, peak learning rate at 0.01, gradient norm clipping set to 0.1, feature dimension of 128, rotating dimension of 4, image, crop size of 224 by 224, cropping strategy of center, and augmentations including flip, color _ jitter, random_resized_crop, and normalize. Evaluation metrics involve clustering the output orientations of the rotating features using k-means and agglomerative clustering methods. The datasets used in this study include 4 shapes and its RGB, D, variants, which are essential for evaluating object discovery metrics. These datasets provide a comprehensive framework for understanding the performance of models with rotating features in various scenarios. Object-centric representation learning models are evaluated using various datasets and baselines. The 10 shapes dataset, a benchmark for object-centric learning, consists of RGBD images with 48 by 48 pixels, each featuring 10 unique shapes in varying orientations and sizes. In contrast, the Pascal VOC dataset, commonly used for object detection and semantic segmentation, is adapted for this study by resizing images to ensure a shorter side of 224 pixels, and applying random horizontal flipping and cropping during training. The model's performance is assessed on the official segmentation validation set with a resolution of 320 by 320 pixels. The FoodSeg 103 dataset, designed for food image segmentation, comprises 4,983 training images and 2,135 test images, with preprocessing steps including random augmentation and rotation by 90 degrees in either direction. The proposed model's performance is compared against several baselines, including the Complex AutoEncoder, CAE, and a standard autoencoder. Block masks, which involve dividing the image into columns and distributing blocks evenly across them, are also employed as a baseline. Furthermore, the performance of other baselines, such as slot attention, slate, Dino k-means, dinosaur transformer, and dinosaur MLP models on the Pascal VOC dataset, are adapted from Seitzer et al. 64, to ensure comparability of findings. This is achieved by adhering to their setup, dataset structure, preprocessing, and Dino pre-trained model. The investigation into the theoretical capacity of rotating features to represent multiple objects simultaneously uses a high-dimensional hypersphere model. It is observed that starting from 10 points and with n large enough, the minimal cosine similarity barely increases, indicating that rotating features should scale effectively to larger numbers of objects. The implementation of slot attention follows the open-source implementation, featuring an architecture with specific layers designed to progressively increase spatial resolution while reducing the number of channels. Additional results showcase object separation in the latent space of a model trained with rotating features. Quantitative and qualitative results for experiments are presented, along with a strong baseline for object discovery on the Pascal VOC dataset. The paper concludes by discussing limitations, assumptions, and potential future work related to the proposed method. This section of the research paper delves into the behavior of minimal cosine similarity between points on a hypersphere, particularly in the context of rotating features. The optimization process for positioning points on an n-dimensional hypersphere is discussed, as there is no exact solution for optimally distributing a variable number of points on higher dimensional hyperspheres. This process involves randomly sampling points and iteratively minimizing the maximum cosine similarity between any pair of points using stochastic gradient descent, SGD. Figure 11 presents the results of this optimization process, demonstrating that regardless of the dimensionality n, it is always possible to separate 2 points by a minimum cosine similarity of 1. However, when n equals 2, corresponding to the setting of the complex autoencoder, the minimal distance between points increases rapidly as more points are added, leading to closely packed and barely separable points when 20 points are placed on the hypersphere. In contrast, with rotating features, larger values of n enable adding more points to the hypersphere while maintaining small minimal cosine similarities. Furthermore, starting from 10 points, if n is sufficiently large, the minimal cosine similarity achievable between points barely increases as more points are added, making it sufficient for the model to separate them. The paper also explores weakly supervised semantic segmentation within the bottleneck of an autoencoder utilizing rotating features. To achieve this, a binary classifier is trained to identify the classes of all objects present in an image during the autoencoder training. A linear layer F class is applied to the latent representation zencoder created by the encoder, mapping the latent dimension of the encoder to the number of possible object classes O. The magnitude from this output is then extracted and rescaled using a linear layer with a sigmoid activation function before applying a binary cross-entropy loss comparing the predicted to the ground truth object labels O. The resulting loss value La class is used alongside the reconstruction loss L to train the network while weighting both loss terms equally. After training, the object separation within the bottleneck of the autoencoder is leveraged to assign each individual pixel a label representing its underlying object class. This is done by measuring the cosine similarity between each pixel in the normalized rotating reconstruction and each value in Z-class for which sigma, Z-class, greater than 0.5. Pixels are then labeled based on the class label of the value in Z-class that they exhibit the highest cosine similarity with. If the maximum cosine similarity to all values in Z-class is lower than a specific threshold, or if parallels of all parallel to less than 0.1, the pixel is assigned to the background label. This procedure does not require any clustering method but directly utilizes the continuous nature of rotating features. Weakly supervised semantic segmentation, WSSS, results, as shown in Table 6, demonstrate strong performance on the MNIST-1 shaped dataset but falter on the MNIST-2 shaped dataset. This dichotomy is intriguing, given the approach's robust object discovery and classification capabilities. The autoencoder setup, comprising a specific architecture, training regimen, and dataset selection, is crucial for understanding these outcomes. Performance metrics such as intersection over union, IOU, adjusted RAND index with background, ARIBG, and accuracy are employed to assess the efficacy of the proposed method, with comparisons drawn against a baseline model. Ablation studies underscore the pivotal role of the binding mechanism in fostering object-centric representations, suggesting its importance in enhancing segmentation accuracy. These findings underscore the complexities inherent in WSSS tasks and the need for further exploration into the interplay between object discovery, classification, and segmentation. Weakly supervised semantic segmentation results are presented on two datasets, MNIST-1 shape and MNIST-2 shape. The proposed approach, leveraging rotating features, demonstrates strong performance by accurately matching ground truth and predicted object colors, as shown in Figure 12. In contrast, the baseline approach randomly assigns labels, resulting in mismatches. While the baseline approach generates accurate object masks, it struggles with correctly predicting labels, as illustrated in Figure 13. Conversely, the proposed approach falls short in creating accurate semantic segmentations, but excels in object labeling accuracy. This underscores the effectiveness of the proposed method in correctly identifying object labels. The comparison highlights the trade-off between object mask accuracy and label correctness. The proposed approach's ability to accurately match object colors and labels demonstrates its potential in weakly supervised semantic segmentation tasks. Figure 14 presents the results of an experiment assessing the impact of the rotation dimension n on object discovery performance in scenes with varying numbers of objects. The rotating features model is evaluated on modified 10 shapes datasets containing between 2 and 10 objects per image. The results show that when n equals 2, the performance of rotating features deteriorates significantly as the number of objects increases, whereas when n equals 10, the performance remains strong. This indicates that the choice of n becomes increasingly important as the number of objects rises. A baseline result for the Pascal VOC dataset is reported, achieving an ARIBG score of 0.499 by simply predicting the same object label for all pixels in an image. This surpasses the highest reported ARIBG score in the literature for this dataset, which is 0.296. However, this baseline performs poorly in terms of MBO scores, with results of 0.205 in MBOI and 0.247 in MBOC. Therefore, the authors focus their evaluation on MBO scores for this dataset. The performance of the rotating features model is also evaluated on the multied sprites and CLEVR datasets, comparing it to its predecessor, the CAE model. The results, presented in Table 8, show that rotating features significantly outperforms CAE, demonstrating good object separation on both datasets. However, the results still lag behind the state-of-the-art. Qualitative examples in figures 15 and 16 illustrate that rotating features encounter the issue of grouping objects of the same color together, which can be addressed by using higher-level input features. A comparative analysis of the CAE and rotating features (RF) models reveals distinct strengths and limitations in object separation on the 4 shapes dataset. Qualitative performance comparisons in Figure 15 demonstrate the RF model's superior object separation capabilities compared to the CAE model, particularly in distinguishing objects based on shape and spatial relationships. However, the RF model struggles to separate objects of the same color, as evident in the rightmost column. This limitation is further illustrated in Figure 16, where the RF model consistently fails to differentiate objects of the same color, despite its ability to learn and separate objects well. These findings highlight the RF model's strength in understanding and representing spatial relationships between objects, but its weakness in recognizing objects based on color cues. In contrast, the CAE model, while less effective at separating objects spatially, may have an advantage in recognizing objects based on color. These insights are valuable for researchers seeking to develop more comprehensive object recognition models that can effectively utilize both spatial and color cues. By understanding the distinct strengths and limitations of each model, researchers can develop more robust object recognition systems that leverage the advantages of both approaches. The page presents the hyperparameters for the rotating features models trained on the multied sprites and CLEVR datasets, as well as their performance results in comparison to the CAE model. Table 7 details the hyperparameters for the rotating features models, including training steps, batch size, learning rate warm-up steps, peak learning rate, gradient norm clipping, feature dimension, rotating dimension, image, crop size, cropping strategy, augmentations, and the number of clusters, K. The multied sprites dataset uses 100,000 training steps, a batch size of 16, and a peak learning rate of 0.001, while the CLEVR dataset uses 30,000 training steps, a batch size of 64, and the same peak learning rate. Both datasets employ a gradient norm clipping of 0.1, feature dimension of 128, rotating dimension of 10, image, crop size of 64 and 128 respectively, random cropping strategy, no augmentations, and K equals 6 for multied sprites and K equals 5 for CLEVR. Table 8 compares the performance of the rotating features and CAE models on the multied sprites and CLEVR datasets, using metrics such as mean squared error, MSE, adjusted rand index with background, ARIBG, and mean boundary overlap, MBOI. The rotating features model outperforms the CAE model in both datasets, achieving lower MSE and higher ARIBG and MBOI scores. For multied sprites, the rotating features model achieves an MSE of 7.082 times 10 to the 4, ARIB of 0.888, and MBOI of 0.863, whereas the CAE model has an MSE of 3.540 times 10 to the 3, ARIB of 0.371, and MBOI of 0.426. Similarly, for CLEVR, the rotating features model shows superior performance with an MSE of 6.643 times 10 to the 4, ARIB of 0.664, and MBOI of 0.608, compared to the CAE model which has an MSE of 1.191 times 10 to the 3, ARIB of 0.289, and MBOI of 0.234. The supplementary section, D7 Additional Results, provides further qualitative and quantitative results for the experiments discussed in the main part of the paper. These include additional qualitative results for the 4 shapes RGB, D, and 10 shapes datasets, as well as the Pascal VOC and FoodSeg 103 datasets. The performance of the rotating features model on the FoodSeg 103 dataset using K-means and agglomerative clustering with various hyperparameters is also compared. The tables on page 27 compare the quantitative performance of the rotating features model across datasets. Table 9 illustrates how performance improves with increasing rotation dimensions, outperforming standard and complex autoencoders. Tables 10 and 11 detail performance on RGB and RGBD datasets, highlighting the impact of color and depth information. Results show that object separation capacity increases with more rotation dimensions and depth information. The figure on page 28 of the research paper presents a qualitative performance comparison on the 4 shapes dataset, focusing on the impact of varying rotation dimensions in the GTAE-CAE model. This comparison aims to assess how increasing the number of learnable parameters influences object reconstruction and separation. The results are depicted through 2 scenarios. One with a rotation dimension of n equals 2 and another with n equals 8. In the scenario where n equals 2, the model exhibits poor performance in terms of object separation and reconstruction quality. This can be attributed to the model's limited capacity to capture complex transformations and relationships between objects in the dataset. Conversely, when the rotation dimension is increased to n equals 8, the model demonstrates a significant improvement in both object separation and reconstruction quality. This suggests that incorporating more learnable parameters enables the model to better understand and represent the transformations and relationships within the dataset, leading to sharper and more accurate reconstructions. This comparison underscores the importance of selecting an appropriate number of learnable parameters in the GTAE-CAE model, as it directly impacts the model's ability to effectively capture and represent complex data transformations. This finding has implications for future research in object recognition and scene understanding, emphasizing the need for careful parameter tuning and model design to achieve optimal performance. The application of rotating features to various datasets, including 4 shapes RGB, D, and 10 shapes, showcases the model's capacity to improve object separation. In the RGBD version of the 4 shapes dataset, Figure 18 demonstrates a significant improvement in object separation with the addition of depth information for each object. However, the model tends to group one of the 4 objects with the background. Figure 19 highlights the model's ability to separate all 10 objects in the 10 shapes dataset by utilizing a sufficiently large rotation dimension n. This increased capacity to represent many objects simultaneously underscores the importance of incorporating multimodal data in object recognition tasks. The performance on the 10 shapes dataset indicates the proposed method's effectiveness in handling complex scenes with multiple objects. The rotation dimension n plays a crucial role, allowing the model to capture and differentiate between objects based on their spatial relationships and orientations. The results demonstrate the potential of the rotating features approach in improving object recognition and segmentation in both simple and complex scenes. Further research is needed to address the issue of grouping objects with the background, particularly in scenarios where depth information is not available or reliable. Rotating features, a novel approach, is applied to the Pascal VOC dataset and FoodSeg 103 dataset, leveraging higher-level input features created by a pre-trained vision transformer. This enables the model to learn to separate objects in real-world images, as depicted in figures 20 and 21, respectively. The efficacy of rotating features is further demonstrated by applying clustering methods to the learned features after training on the FoodSeg 103 dataset. Figure 22 illustrates the results of k-means and agglomerative clustering methods, with mean and standard error of the mean, SEM, calculated across 4 seeds. Notably, k-means clustering achieves better performance, but agglomerative clustering eliminates the requirement to set the number of objects to be separated, offering a trade-off between performance and convenience. The clustering methods are evaluated using a distance threshold, with k-means clustering achieving optimal results at a threshold of around 0.30.4, as shown in Figure 22. This suggests that rotating features can automatically learn to separate the appropriate amount of objects, allowing for efficient testing of various clustering methods and hyperparameters after training. Overall, this page highlights the capabilities of rotating features in real-world image datasets and demonstrates its potential for efficient object separation using clustering methods.